Good morning. Last week we started describing the three-dimensional protocol layer architecture of broadband ISDN, which is organized in three planes: the user, the control, and the management. And the user for the data transfer of the user data, the control for the signaling, opening, managing, and closing virtual circuits, and the management for coordination, monitoring, etc., etc. Now, let's focus again a little bit more on the user plane. And in the user plane, we see again, as in frame relay, the similar approach which was defined at the time, core and edge, which basically means keep the core of the network simple, which means reduce the functionalities you run within the cloud, within the network, so within the nodes, switching nodes, and put the complexity or the more sophisticated functions in the end system, which are labeled as user terminal. Now then, what the user terminal really means in practical network, that's another matter, but from the perspective of frame relay and broadband ISDN, user terminal were really user terminal. And if you compare the three scenarios that you have described up to now, we have comparing in the same slide here the ISDN, the frame relay, and the broadband ISDN. You see that there is a simplification. First of all, in the number of layers, we reduce the number of layers. Started with 3 and moving to 2, and then these 2 layers are partitioned in 2 sub-layers. Only one of the 2 is really active within each node within the network, which is the DL core part in frame relay and the ATM protocol in broadband ISDN. And end-to-end, we have a simplification of the functionalities, because end-to-end, the error control via retransmission is existing in frame relay, but it's optional, so you don't have to use it. You can, but you don't have. Whereas end-to-end in ATM, or in broadband ISDN, to be more precise, more formal, we have only the error detection capability end-to-end, and not for all the AAL layers that we will see. There are several protocols which are named AAL, and some of them have only the error detection capability. So there is no error control in the sense that there is no error retransmission. So we are not dealing with errors at this level of the protocol layer. Of course, if this feature of correctness or reliability is important for your application, you will have higher layer protocols that will deal with that, but not in the lower layer of the protocol stack. That's the basic idea. Okay? You have any question about that? So now let's focus a little bit more with some details on the specific layers. We have said a lot about the physical layer. PDH and SDH are typical physical layers that have been defined or redefined, or if you want, what's the English name of that? They've been adopted within the standards developed within the broadband ISDN. There are also other physical layers that have been designed, but actually they didn't find such a large, wide applicability. And then we'll look a little bit at the ATM layer, whose main features are, of course, switching and multiplexing. We have a rate adaptation feature between the physical layer and the above layer, which is called AAL. AAL stands for ATM adaptation layer. We will see in a moment what is dealing with. And at the ATM protocol layer, we are dealing with different types of cells. We have data cells or user cells. We have operation and maintenance cells, and we have resource management cells. We will see later in the class that resource management cells play a key role in some of the algorithmic features that have been designed to provide QoS in the broadband ISDN arena. So some of those techniques rely on the use of particular cells which are called resource management cells, which allows us to control the traffic generation process at the user premise, at the user access. Okay, and those are called resource management cells. Operation and maintenance instead are cells used to do management and this type of features on the virtual circuit. In terms of format, we see something different from the other architectures. Both ISDN and frame relay envision variable packet size of significantly large value. The largest packet size in frame relay is 4,000 bytes, just to give you some numbers, so 4096 to be more precise. That's the maximum packet size, and it's of variable size. So depending on your needs, you can generate a packet of variable size up to 4096. Here, the packet size at the ATM, which is the layer 2, the bottom part of the layer 2, is very, very small. We are talking about 53 bytes. Okay, 53 bytes is a very small packet size, and in particular of those 53 bytes, 5 bytes are for the header, and 48 bytes are for the payload, so carrying user data. Okay? It means that basically, in order to be able to transfer packets generated by the user on the ATM network, we will need to run a segmentation process. We need to take the packet size, which typically will be larger. So suppose that on top of this architecture we have IP protocol. We will have an IP packet of typically larger size, and we have to chop it and to make a set of 48-byte cells, one after the other one. Okay, we will see that a little bit with more details later. And why is that? So always try to get the motivation why this choice has been made. If you remember, we have characterized the broadband ISDN saying that it's the real first attempt, and I would say also the only attempt, of designing from scratch an integrated network. So integrated network means I need to have a single architecture, not only in terms of infrastructure, but also in terms of set of protocols, which is able to solve any user need through applications run by the user. Okay? And at that time, we are talking about the 90s here, early 90s, when the broadband ISDN where standardization process started. It ended out about 10 years later. So last decade of the century. At that time, two most important type of traffic were data traffic, which include a variety of applications, of course, already at the time, not so many as today, but there were several applications run, but all of them oriented to transfer the data among PCs, computers, workstation, whatever, and telephone networks, voice, human voice. Okay? At that time, the human voice was significantly dominating in terms of percentage of traffic. Today is not the case anymore, but at that time it was really significant. And so the first objective of this integrated network was to make choices that were good enough, at least for voice calls and data traffic at the same time. We know that this is not easy. Why is that? Basically because voice and data have different requirements in terms of what you want to obtain from the network. Let's see if there is any. No, there is no slide. There is no slide about that. Sorry. Just to keep it simple, the most important thing when you make a phone call, and that's the reason why the telephone network is using circuit switching, is the minimization of the delay. We don't need a large bit rate. 64 kilobits per second is largely enough. With some clever compression techniques, we can get less than that. Okay. So the bit rate is very little for a phone call. The error probability is not a nightmare. I mean, we can tolerate some errors in the voice transmission, okay, if you don't compress it, if you don't use peculiar coding techniques, whereas the delay is very important. Okay, we need to have an end-to-end delay which is as small as possible to make the phone call really interactive. Otherwise, it sometimes happens, these days a little bit less, but up to 10 years it was fairly common when you make an international phone call, very easily you will get a satellite connection. And the satellite connection means that the voice signal goes up to 36,000 kilometers to the satellite and then back again, which makes an end-to-end delay which is non-negligible, just for propagation. And in that case, the phone conversation started to become a little bit painful because you start talking, then you stop, and when you stop, the other end has not yet received your voice, so it doesn't know exactly that at that time you have stopped. So there is a delay, a lag, and in this lag, maybe the two speakers start speaking at the same time because you are expecting like an okay, right, from the other end, and it's not, you are not getting it, so you start talking, and in the meantime, the other end started talking again, and then you have the voice. So it's kind of, you have to talk in a kind of a walkie-talkie mode, which is not really natural to the phone, right? And that happens when the delay is too large. Too large means, roughly speaking, larger than 100 milliseconds. That's very, very, very annoying on a phone call. And that's why all of the effort in the telephone network are put in minimizing the delay. The only delay that you have is propagation. That's a physical limitation. There is nothing we can do to avoid it, but that's the only delay we have. On the other hand, for data traffic, the delay is not so important. Who cares about the delay of a single packet? We don't really care. It's important the bit rate, how fast we are able to exchange information, if you think about file transfer, for example, okay? So, two different requirements, and also the choice that you will make would really be different, okay? If you want to minimize the delay, what you have to do? To store in the intermediate node as little as possible, right? Because remember, storing implies delay. It implies transmission and reception delay, it implies queuing delays, so we would like to avoid it, all right? So for the voice traffic, storing data in a node is not a good idea, and that's why circuit switching, because we are not storing anything there, right? On the other hand, if you want to have a small loss probability, because you want to have reliability, you want to have high bit rate, you want to avoid retransmission, the more you store in the intermediate node, the less packet you have to drop, right? And so it's easier to ensure reliability without controlling tightly the network by increasing the buffer size. But if you increase the buffer size, you increase the delay. So this is just a trivial example that should be enough to understand which are the difficulties in designing an integrated network, okay? Now, having that in mind, if you want to support efficiently voice traffic, we need to have small packet size. And why is that? Well, first reason, we want to reduce the latency while we are crossing a node. If you remember, I'm sure you do, but just in case you are not right on target, if you remember when we have depicted what's happening in packet switching, we have a scenario like this one, right? So this is the packet transmission on the first link, then you receive it, and then you transmit the packet on the next link, and so on and so forth, right? This is what's happening in packet switching if you have a large packet size. Now suppose that you divide this packet in three. Okay, what's happening? Well, actually, it's in three. When you get the first packet, you can start sending on the second link, and you get the so-called pipeline effect. So what's happening is that you can start sending part of your bits earlier on the next link because you have a smaller packet, right? So you reduce the latency. You see, the green latency is in the order of packet transmission time. If you reduce the packet size, of course the transmission size of each smaller packet is reduced, and you reduce the latency, the delay that you have in crossing the node. So that's the main one of the reasons why you may want to have a small packet size, because a small packet size implies a small latency crossing the nodes. Okay? Yes? Yeah, of course, yeah. That picture is not correct, completely correct, because as long as you chop the data in more data units, you have to add an header to each of them. So it's not, this picture is not fully correct. You are right. If you have a single packet, you have only one header. If you have three packets, you will have three headers. So you end up sending a little bit more. So there is, of course, there is a compromise there. You cannot go to a packet size of 1 bit. Okay, this is not correct. So you are right, absolutely. So, but again, up to the limit in which the ratio between the header and the data size is significantly good, so 10% of header, it's better to have smaller packet in terms of latency. Okay, there is a limit in that. Yeah, you are right, absolutely. Okay, so that's one reason why you may want to take the packet size small. It's not the main reason. And why is that? Because there is another way in which you can reduce this delay. And the other way is to increase the link speed. Now, it's always true that the smaller the packet size in bits, the smaller the transmission time, obviously. But since we are talking about delays of the order of hundreds of milliseconds, which is the human perception of delay when we talk, if we increase the bit rate of the link, yeah, if the packet size is reduced by a factor of 10, you are reducing the delay by a factor of 10, for sure. But if the delay is already few microseconds or few nanoseconds, it doesn't matter. So you can reduce this latency by increasing the link speed. And we are talking about broadband ISDN, and broadband ISDN, the link speed is very high. So if you have a very high link speed, it is true that by reducing the packet size in bits, you reduce the latency, but the latency is already so small that we may say it's not a big issue. Okay? So it's not the main reason why having a small packet size today, because you can compensate it by increasing the link speed. So if you want to add a note to your slides here, which it's written actually. So the reduced latency gives in favor for the small cell size, but it can be obtained by increasing the transmission speed of the link. So there is another way of obtaining this reduced latency. Okay? What is really important for voice is the second point here, which is called packetization delay. Now, what is the packetization delay? It's the time needed to build the packet at the source. Let me see, well, what does it mean? Well, normally for data traffic it means nothing, but for voice traffic it means something. Remember, as a first approximation, so let's not consider sophisticated coding schemes, we have a voice signal which is something like that, okay? It's an analog signal, and what we do? We sample it, right? We take samples. No. With a given frequency, we take samples, and then for each sample, what we do is that we represent each samples in 8-bit. Remember that? It's 8-bit, 8,000 samples per second. It makes 64 kilobits per second as a bit rate, okay? So every sample is 8-bit, okay? Now, if you want to send these on the phone network, which is secret switching, you take the sample 8-bit and you send, and then you take a sample every 125 microseconds, you send 8 bits, and this is what you do continuously, right? We cannot do that if we are sending packets. We cannot create a packet of 8 bits. It doesn't make any sense. So what we can do is that we start collecting a given amount of samples to build the packet, or the cell in our case, okay? So the packet is built by collecting samples, voice samples. And the speed of collection of voice sample is not depending on the link speed or anything, it's depending on the human voice. We need to sample at that speed, 125 microseconds. We could sample faster, it's completely useless. There is no gain. So that's the nature of the signal, and we have to sample at that speed. Anything faster you can do, but it's not useful. It doesn't give you any improvement. You are simply enlarging the amount of bits that you send with no gain in terms of ability of rebuilding the original signal. So that means that the larger the packet you have to build before sending it, the more time the first sample in the packet has to wait. So if the packet size is 80 bits, you have to wait for 10 times 125 microseconds, 10 samples at that speed. If the packet is 800 bits, you have to wait 100 times 125 microseconds. 100 times 125 microseconds, which is a larger time. That's called packetization delay. The time needed at the source to build the packet. You cannot speed up this process. There is nothing you can do to speed up this process. That depends on the nature, on the characteristic of the human voice. So from that perspective, the only way of keeping that delay at the source small is to have a small packet size. And that's why the small packet size has been chosen. And really, 48 is very small. Clear to everybody? Okay, so that's why 48 is coming out now. Why 48 and not 64 or not 24? That depends. I mean, doesn't matter. Okay, there were reasons why that number was chosen, but at the end, the concept is that it's small. And that has two drawbacks. First drawback, well, 5 bytes of header over 48, 10% overhead for only one protocol layer. So only at the ATM layer you are losing 10% of the link capacity. Losing in the sense that you are not using it for data transfer generated by the user. That's the first observation. Of course, this ratio would become better if we had a larger packet size. So that's an example of compromise choice, right? We have fixed a small packet size to ensure a good quality for the voice. The negative effect is that the ability of exploiting the link capacity is reduced. So we are losing roughly a little bit more actually than 10% only at the ATM layer. Okay? And that's wasted on any application regardless of anything else, just for the packet format. Okay? But there is even something worse, which is the so-called segmentation overhead. What is the segmentation overhead? I will try to explain through an example. So let me compare two scenarios. We are generating packets and we have two scenarios. In one scenario, the packet size is large. So let me call frame relay scenario, okay? So we have a large packet size. So we have a node, we have an output link. Suppose we have, I don't know, 5. So this is frame relay. We have 5 packets coming in at different inputs, okay? And we have a given buffer here. And suppose that this buffer size has 3 positions available. 3 packets can be stored. Okay? So we have a given amount of buffer space which is occupied by packets we have received in the past, and we can store 3 packets more. Okay? And we get 5. And all of them want to go on this output link. Is it clear? Now what we will do? Well, we will take 3 out of 5 and we will store, and we will drop 2. Which one? I don't know. It depends on the contention resolution algorithm that you use. It may be random. Maybe the packets are arriving not exactly at the same time, so you will get the 3 that arrive first. It doesn't matter. We take 3, we store, and 2 we drop. Okay? Clear? So suppose we drop this one and this one here. So we have 2 packets dropped in this node. Okay? Now let's consider the same scenario. So the same resources available, the same situation for ATM. So we have a buffer here. Now we are installing cells. So we suppose that 1 packet becomes 100 cells. Okay? So suppose that, yeah. You have a question? I mean, if you have, let's try to keep the lesson a little bit interactive. So if you have doubt, don't worry, just raise your hand and ask me. Yeah. I'm not sure I got the question. It is a protocol layer, yes. Not, sorry? I don't understand. That was a joke about ATM. Come on. Automatic, it is not called ATM in Italy, it's called Bancomat, you know. Okay, so no, it's a protocol, yep. So, I suppose that 1 packet size is, I will sign your name, of course, you will take 3 grades less during the examination, or this bad joke. Okay, so suppose that 1 packet is equivalent to 100 cells in terms of size. So what's happening here is that you get 5 trains of cells here on each link of 100 cells, each of them, right? Roughly speaking, more or less back to back, because you have the packet, you take the original packet, you chop it in 100 cells, and you send the 100 cells one after the other one, okay? So this node will receive trains of 100 cells on the 5 links. Clear up to now? Now, we have here space for what? 300 cells, if we are in the same conditions, right? The same amount of buffer size. We can store 3 packets in the first case, we can store up to 300 cells here, okay? And if you don't do anything special, what's going to happen is that you will start getting cells from all of the packets until you have space in your buffer. And when you have saturated the buffer, you will start dropping cells. And at the end, you will end up dropping, statistically speaking, the tails of all of those, right? The tail, I mean, the last cells in each of these 5 trains of cells. Statistically speaking, not exactly the same number of cells from all of them, but very likely you will drop cells from all of the 5 packets. And what's going to happen here is that those partial trains of cell, which have some cell lost, will go through the network, will be received, and will drop all of them at the receiving end, because when you chop a packet, remember that if in a given point of your network you have this packet, and you chop it in, I don't know, in this example, whatever number it comes out, even if you drop one portion of that packet, when at the receiving end you try to rebuild it, there is something missing and you drop everything. So a single segment or a segment cell in our example dropped means that all of the other one will be dropped at the receiving end because you're not able to rebuild the original packet. That's one of the negative effects of segmentation. Besides what you said before, that when we are going to segment, we will have more overhead. So that's another issue. So we are not even considering that. But even if you don't consider the additional overhead, we are much more prone to drops with two negative consequences. First of all, we are going through the network to send cells belonging to packets which are useless from the user, because when you will get them, you will drop. So we are occupying network resources for something that will not be useful for the user, which is not the case in the previous example. In the previous example, you fully store 3 packets. So those 3 packets will be good, will be transferred, of course, if there are no other losses, to the user, and you will get that as good boot, what is called good boot, something good for the user, right? The other 2 are dropped. So the total amount of bits we drop is the same, because we are in the same condition, the same amount of bits, the same available buffer space. But we are dropping in a more clever way in the first case. So the second case is generating more overhead. We are not looking at that. It's creating what is called useless traffic, traffic that we carry in our network with no real usefulness for anybody. And then we have a larger drop probability, because statistically, in the first case, we have dropped 3 packets. In the second case, we will drop 5 at the receiving end. So we have a larger drop in probability. So there is really no gain in the segmentation process. There is no gain, not only for ATM. In general, whenever you need to segment, you need to fragment, that's not a good thing. You have to do that, okay, you will do that, but if you can avoid it, it's much better to avoid it. Okay? We cannot avoid it here in the ATM layer, because packet size is 48 bytes. So unless the original packet is very little, very small, we will have a segmentation process almost for sure. Okay? And that's the negative consequence. So that's very good, very bad, for example, for data traffic. Again, the segmentation process is not good for data traffic. Any question? Yes.
Why they chose to what meant to be like an integrated network? Why they chose to fix the size of the packet? Why they let like small packet for voice and big packet?
Yeah, that's a good point. The question I repeated because otherwise for the registration you will not hear it. The question is, why not having a variable packet size? That's a possibility, which means a small packet size for the voice and larger packet size for the header. That could have been a choice. The main reason why that was not done is that at that time, so it's the historical perspective, building a switching device acting on fixed packet size was much easier than building a switching device acting on variable packet size. That was the main reason why this technology used that. Okay, so that was really a technological choice. For many years that was true. I would say for about 20 years it's really true that if you want to go very high speed, it's much better to have fixed size data units, because the switch in such a way that you have a timing behavior. You go to the input, you will see that either you receive a packet or a cell or not at any input, and you have to make the transfer of n data units of the same size at the given time instant to the output. And then you regenerate the system and you go again back after 1 cell time, and you can make the operation of the switch synchronous. And that for many years translated in much faster switching device. And remember, that's broadband. We need to run at high speed. So that was the main reason. Today is slightly less true. There are techniques that allow us to have asynchronous switches operating almost as fast as synchronous one, but at that time it was not true. And that was so true that even for IP routers, which naturally operate on variable packet size, because the IP packet is variable in nature, internally they were switching or routing or forwarding, whatever you want to call it, using ATM chips, which were operating on fixed size data units. So you get the IP packet, you chop internally to the switch. There is nothing that has to do with the protocol layer on the link. Internal to the device, you take this IP packet, you chop in 48 bytes ATM cell, you had an ATM switching internally, moving cells from input to output, and then before sending it out, you were rebuilding the IP packet at the output. That's because it was so more efficient to do the switching at very high speed in fixed size data units. So even IP router for many years, the high performance one, the high end, were operating in that way internally, which has nothing to do with the protocol format, which is what we are talking about here. Okay? Yes?
So basically, at the very end, ATM was optimized for voice. I mean, they were more interested in voice rather than in data traffic, actually.
From the protocol, well, from the protocol layer architecture, you may say that that is true, in the sense that if you don't make this choice, you will basically cutting completely off the voice market from this technology, okay? Whereas for the data traffic, it's not that it's not working, okay? It's not the best thing that you can do, but still it was very efficient. You have to take into account that when ATM switches were built or were sold on the market, they were almost 10 times faster than any other switching technology. And so you mean it was good also for data traffic. So it's partly true, it's only partly true. Now you can say that from the historical perspective, at that time that was not true. Because with this constraint, we were able to go a very high speed, and so we were able to provide high speed also to data traffic. Otherwise, we would not be able to do that in any case. So it's
because the rate of data traffic, the dimension is not comparable with the one of today.
At that time, it was not comparable. And the other, if you want, the other reason is that ATM has been designed mainly by people coming from the telecommunication industry, so from the telephone guys, AT&T at that time, which were the big player at that time. So they were not coming from the computer science part or the internet or whatever. So that's also part of the reason. So they were actually trying to avoid getting put away from the market, the future market, because at that time it was clear that as a perspective, the data traffic in maybe 5–10 years, nobody was sure about the time, but for sure it was become dominant. So to avoid to be completely cut off, that was the attempt. It didn't work. It didn't work at all. At the end, it didn't work, but that was the idea. Okay? Still, ATM is a very important technology from our perspective because most of the layer 2s today, as I said, I think at the very first lesson, are running either on frame relay, but less popular, ATM, and gigabit Ethernet. These are the three technologies that at the lower layer are used in the internet, so for carrying data traffic. Okay? And so that was the integration that actually happened. We are integrating two completely different worlds. The internet was designed without taking any care about layer 2. And then we had a lot of layer 2 technology trying to do something up to the point of becoming a single dominant network, which we didn't succeed. And today they are running together. They are working together. So we have also to think about what's the consequence in terms of interplay and these kind of things. Okay? Any other question? Okay, so that's the ATM cell format. What would you expect to see in the header according to the features that we know that they are in ATM? So there is no error detection, remember, because the error detection is only optionally at the AAL error, end-to-end. So what you would expect to see in this packet header? We have basically only one thing, which is what? Sorry? Yeah, the label. We need the space to label the packets because this is a virtual secret. And indeed, if you look at the packet format, you will see that basically, let me jump some details. Basically here we have let's forget about GFC, which is available only at the user to network interface. So on the access, there is a slight mismatch between the two packet formats. It doesn't matter. It's not so important. Let's forget about it. We have VPI and VCI, and this is 5 bytes, so it's 12 bytes of VPI and 16 bits. 12 bits of VPI and 16 bits of VCI, which are the two labels for the virtual secret, so group and virtual secret identifier. They are called VPI and VCI. There is one priority bit with very similar meaning and idea as the one we have seen in friend relay. Do you remember there is one discard eligibility bit in friend relay to have high and low priority traffic within a virtual circuit? Okay? And for several possible use, and there is 1 byte of header correction. Now, as I said at the beginning, we have different level of ways of dealing with errors, and when we say that this protocol is not running any error control, which is the case of ATM, typically still we have an error detection capability on the header. Why? Because on the header we have the addresses, so we want to avoid having wrong addresses, because a wrong address means giving this data to the wrong destination, and that's something we want really to avoid. So there is an error detection and also correction capability, in this case, on the header. Only on the header, not on the data. In the data we do nothing. So we are able to detect single errors, we are able to detect multiple errors, and we are able to correct single errors. And you see 1 byte to protect 4. It's a large overhead. It's a very large overhead. If you go back to the friend relay, the error detection field was, I don't remember, a couple of bytes to protect thousands of bytes. Sorry, not to protect in the sense to be able to detect errors on thousands of bytes. Here we have 1 byte to protect 4. So it's a strong error detection, and also it's an error correction capability. So we may correct errors in the headers, which are still unlikely normally because we have fibers, high good quality medium. Okay? And that's basically it. There are slides which summarize the meaning of the various fields, of course. You can find the documentation. There is one field we have not described yet, which is the payload type. And the payload type is there to allow you to distinguish between different types of cells within a virtual circuit. As I said, there are 3 types of cells: data, which are carrying user data; operation and maintenance, management of the virtual circuit. Okay? Normally, in a user virtual circuit, these type of cells are not so popular, but I mean, we may have virtual circuits that carry control information, management information, that may instead use significantly operation and maintenance cells. So we need to distinguish them. Okay? And then we have the resource management cells. Cells used to control the user traffic process of generation data, of data generation. Okay? So if you go a little bit down a few slides, you will have, this is the more detailed description of what the payload type, which is 3 bits, means. If the first bit is 0, this is a user cell. Okay? We will come back to a moment for the other bits. If instead it is 1, depending on the code, it may be a different type of operation and maintenance cell, or the resource management cells I was mentioning before, to control the user flow. Okay? If it is a user cell, the first bit is 0, 1 bit is devoted to signaling congestion, like we have seen in friend relay. If you remember, in friend relay we have 2 bits, forward and backward, to signal congestion. Exactly the same here. We have 1 bit to signal congestion to the user on that virtual circuit. It's a very selective signaling scheme. We are signaling independently for each virtual circuit, because this bit is in the header, and this header contains the label. So for every label we can say we are congested, we are not congested. It depends on the node, on the network to do that, depending on to which virtual circuit you want to do that, but you have the flexibility of signaling that per virtual circuit, specifically independently for each virtual circuit. Like in friend relay, it's the same thing. And there is another bit which is used, we will see later in a moment why, for AAL. For one of the AAL, we'll exploit 1 bit, the black one here, for an operation that I will describe later. Okay? Any question about that? So that's basically it. These are a set of functions that you run at the ATM layer. So cell type discrimination, explicit congestion notification. You may have user parameter control to that field we have not seen. We have the management of the priority bit, okay, and so on and so forth. Not so important. Can I go? Okay. Okay, AAL. Do you have any joke about AAL acronyms? Anybody? Okay, so AAL stands for ATM Adaptation Layer, and it's adapting, so it has one main feature, to run the segmentation process when you transmit the data, and to run the reassembly process when you receive the data, because we know that on the upper layer we will have packets of significantly large size, and the ATM layer is only 48 bytes. So one of the main goals of AAL is to do segmentation and reassembly for ATM. So we'll need to have rules to take the large packet size and to chop in integer multiple of 48 bytes, but with the ability of putting those chops, those cells, together at the receiving end. The AAL, which remember is running on the terminal, user to user. So at the user you chop, and at the user receive you have to put everything together again. Okay? So that's one of the main features of AAL, segmentation and reassembly. And then there are other things. And why there are other things? Well, because AAL is the first example we see of a protocol which is actually a set of protocols. So there are several AALs, and when you open a virtual circuit in Broadband ASDN, you can select the AAL that better suits your needs. Okay? Now, if you go back to this picture here, where is it? This one here. Take the, let's take this one, which is easier. Okay? That user terminal here, at least in the original idea of this type of architecture, was really a user terminal. Okay? So this architecture has been designed having in mind that the network was going to be ATM or ATM plus AL, whatever, end-to-end, user to user, no other technologies in between. That was the original idea. So that user terminal was really user. Okay? And if you look at this picture, and if you remember, I hope that some of you do, not all of you, I'm sure, if you go back to the very first picture that we have seen in terms of protocol architectures, okay, it was a couple of lessons ago, in that picture we have seen an architecture with 7 layers. And we had 3 layers in any node, and 4 top layers only in the user. 7, 6, 4, and 5 only in the user. And there was a layer which was called transport, which was the first layer not available in the network, but only in the user. That was called transport layer. If you look at this picture here, the AAL is the first layer not present in the network. So it's very similar, if this is a real user, to what is a transport layer in a typical packet switching architecture. Okay? So it's the first layer end-to-end, not running in your network. AAL is not running in your network. It's not running in your switches. It's only running in the user. And on top of that, we had in mind, people designing this architecture had in mind that users were running applications directly on top of AAL. That was the original design. Okay? So you have user terminal, users running applications, whatever application you have in mind, and then when you want to send the data for this application, you had AAL dealing with that. Okay? Is it clear? Now, given that, of course, different applications may have different needs. And that's why we are not able to satisfy all of the needs with a single protocol. That's why there are 4 protocols that have been defined. 4 AALs, having in mind different, of course, not single applications, but family of applications, type of applications you may need to run. Okay? So, is it clear, the picture here? So, basically, the 4 AAL that have been defined having in mind the so-called 4 classes of service. Let's forget about the terminology. Different type of applications, different type of needs, and they are called AAL 1, 2, 5, and then 3, 4, because originally there were 5 and then 3 and 4 were merged in only one. So it's AL1, AL2, AL3, 4, and AL5. And AL1 is meant to provide services to voice and video of uncompressed application. So you take a voice, video, of course, of a small size, and you send it in an uncompressed way. Okay? So it takes the signals of the human voice, you take the 8 bits, you put 8 bits together for 48 times, you create an ATM cell, and then you send it. Okay? The video, you may have video at small bit rate, which means you have a small picture of a limited number of pixels, a limited number of writes, so the resolution is very limited in order to keep the bit rate small. Okay? Just to give you an idea, we will see that a little bit later when we revise some coding techniques. A TV video channel, not HD TV, just a plain TV, the old television system, a color-based TV channel. For a single TV channel, it requires, if you don't compress it, roughly 300 megabits per second. A single TV channel roughly needs 300 megabits per second at full TV resolution, not HD TV, plain TV. Okay? So PAL systems, CAM system, or NTSC system in the US, which is a huge bitrate, very large. Okay? Now, if you compress it, the number becomes much smaller, but then you need to run compression techniques. We will discuss about compression technique a little bit later. AAL2, similar. It's for voice and video, but having in mind larger bitrate and compressed, which means that it's not constant, the generation process, but is variable. And then 2 AAL for data traffic. Okay? Now, I don't want to go into too many details, and this is provided, these functionalities are provided for the different AALs in the so-called convergence sublayer, which is part of the AAL. The other part is segmentation and reassembly, which is doing what we have said before. Take the data, chop it, and then reassembly at the receiving end. Okay? So which are the main functions available to the applications for AAL1, 2, 3, 4, and 5, besides segmentation and reassembly, which is available for all of them? Well, in some cases we need error detection, especially for data traffic, so we have error detection. For voice and video application, there is something which is very important. I'm sorry that there is not a slide here, but this is good so that will force me to reduce this emission rate a little bit. And let me describe which are the issues that you may have with multimedia signal. Let me see if I can exploit. Yeah, I think we can exploit this a little. No, not really. Okay, so let's go back to this picture here. So let's take a very trivial multimedia signal. Let's take the voice sample example again. So we have this voice signal, we sample it. And then from this we will derive, we will derive something like that. Why is that? Well, because, of course with a given delay, because we are generating sample at a constant rate, right? One sample every 125 microseconds. This space here between two samples is 125 microseconds. Okay? So in order to build a fixed size packet, we will take a given fixed amount of time, so we will generate packets on a regular basis. And in particular, this spacing here between two consecutive packets, if this is a voice, is going to be 48 times 125 microseconds. You agree on that? Why is that? because we need to put together 48 samples, and that's the time required to do that. So the spacing between consecutive packets is exactly this one, at the source. Okay? Now, what we need to do at the receiving end? Well, we need to, with a given delay, of course, which is depending on how far we are, we would like to reproduce this packet generation process, correct, from which we will derive this analog signal, extracting the samples and spacing them properly. But we need to rebuild this time sequence of packet generation, and from this derive the sample sequence. Okay, so this is the transmitter, and this is the receiver. Now, what we have in between here is a network, and actually the receiver is not going to receive something like that. In a circuit switching network, that's exactly what's happening. The packet size is 8 bits, you generate regularly, all of the packets get the same delay, you will receive the packet spaced in the proper way, and you can play them back with this spacing, no problem, because the delay is fixed for every data. So it's the network which ensures the proper synchronization among packets, which in that case are 8 bits only. Clear? This is not what's happening with the packet switching network. In a packet switching network, you will get this, and you will receive packets in something like that, probably, with the spacing which is random among samples, right? Depends on what? It depends on the delay that each packet is going to suffer. The propagation delay is fixed, of course. The transmission delay is also fixed, but the variability is due to the queuing delay. So in general, if you're running a multimedia application, in this case it's a voice, but it can be a video, it can be anything you like, you generate packets on a regular basis, but then the network destroys this shape, changes it due to the queuing delay. So this is due to the queuing in the node. And we don't know whether we will have queuing or not, but we cannot take for granted that there is no queuing. If there was no queuing, we will have exactly the perfect spacing at the receiving end. In general, it's not the case. So the receiving end must rebuild this ordering, okay, from this strangely delayed packet sequence. Okay? So in order to do that, you need some information. First of all, you need to put packet in the proper order, and that's called sequence number. Why? Because in principle, depends on the network you have in mind, you may even have packets following different paths with different delays, so a packet generated later may overtake through a different path a packet generated earlier. So you may get packet 5 earlier than packet 3, in principle. It may not happen, but in principle you must be able to deal with that. Okay? So you need a sequence number to make sure that you put packet in the proper ordering, and then you need to space them. And in order to be able to do that, you need to know which is the logical time, which is called timestamp, at which this sample has been generated. Okay? So that packet has been generated at timestamp. So let's start timestamp conventionally from 0 at time 0, the next one at time 1, the next one at time 2, etc., etc. And that allows you to space the packets in a proper way. Okay? Any question about that? You should have some question, because my explanation was a little bit superficial and not completely precise. So basically we need two things. First of all, to put the packet in the proper ordering through the sequence number, and second, to put the packet with the proper spacing to the timestamp. Okay, clear? Everybody convinced about that? You are not fully convinced. Yeah, this is for packet switching network. We are talking about AAL, which is packet based, so AAL on top of ATM. Who is not fully convinced? Well, let me put these things in this way. Let me ask you a question. Do we really need both of them? I mean, what's going to be a sequence number in this example here? It's going to be 0, 1, 2, 3, 4, 5, right? And what's going to be the timestamp? Well, suppose that we start again from 0. We can start from any conventional number. The timestamp is going to be 0, 1, 2, 3, 4, 5, 6, 7, etc., right? So it's going to be the same. Does it make sense? And the reason is yes. It makes sense for two main reasons. First of all, that's a very trivial example of coding. There are coding in which, for example, suppose that in your voice signal there is a silence. Okay? That's a man who is speaking, right? Sometimes, not me. I'm a man, but I keep speaking forever. But normally men speak a little bit less at the phone than female. So there is a pause in the speech, right? You are not saying anything. Okay? So you may say, I don't care. I keep sampling the signal, and I will generate 8 bits and will send it. That's what you do in the basic coding technique. Even if there is silence, you sample the silence and you send it. Okay? You don't want to take care about what's the meaning. The other alternative will say, well, no, I detect this signal here, this silence, and I will not send the sample. Now, if you don't send the samples, you will have something in which the sequence number, suppose that this sequence number was 3, this sequence number will be 4. That's the next packet. But in terms of timestamp, that's not 4, because there is more time between the two. So that timestamp may be 5, 6, or 7, or whatever. Because conceptually, the sequence and the timestamp are two different things. So there are scenarios in which they have the same value. They may have the same values. For example, regular sampling generation, okay? But there are other cases, and this is called silence suppression, in which is not the case. Silence suppression. If you use this coding technique, you may have some timestamp which are missing. So one packet may have a timestamp 3, and the next one may have packet timestamp 8. And it's important to have this number to space properly them at the receiving end. That's the only way of spacing them in the proper way. If you don't have the timestamp, you have no idea of how to space them. Is it clear? Other example, you may have several packets generated at the same time. Suppose that this is a video. When you send the video information, okay, this frame should be sent, it's generated at the same timestamp, and should be played back at the same time, right? To show that frame in the picture, that picture in the video, okay? All of the packets should be shown with the same timestamp, and they are actually generated with the same timestamp. Still, they have a sequence between them. You have to put in the proper ordering. So in that case, the sequence number will be different for every packet, and the timestamp will be the same. That's the logical time at which these packets have been generated, and you generate them at the same time. And you have to play them back at the same time. Okay? Clear? Okay, the last observation, then we should have a short break, is that there is another subtle issue here, which is clock recovery. Now, if you remember, we have already talked about clock recovery when we said about digital transmission on a point-to-point link. In that case, we generate bits. We have to detect at the receiver whether you have sent a 0 or a 1, and if you are able to do that and coping with the noise, we are basically neglecting the noise on the channel because we are able to rebuild the proper sequence of 0 and 1. And in order to do that, we must have at the receiving end a proper bit information, bit time information. Because if your clock is different from my clock, then sooner or later there will be a mismatch. Okay? And that's not good. So on a point-to-point link, for transmission purposes, we will have mechanism of recovering at the receiving end the clock of the transmitter, link by link. We have seen that in PDH, in SDH, and all these kind of things. Okay? Now here we have a similar issue. It's not a physical link, but the receiving user, in order to play it back properly, exploiting the timestamp on the packets, must have the same clock of the source. Because if the two clocks are slightly different, sooner or later, if I'm a little bit fast, sooner or later there will be some data missing, if the communication lasts for a long time, or on the other hand, we will keep increasing the delay at the receiving end, if there is a mismatch between the user to user clock. So we will need some mechanism of sending synchronization information among users. It's not going to be so tight in terms of timing like in a point-to-point 1 gigabit link, of course. We don't need to have a perfect clock synchronization bit by bit, we don't care. but the two clocks must match. So some of the AAL, in particular the AAL 1 and 2, provide these features: synchronization recovery, timestamping, sequence numbering, okay? Which are the most important features for multimedia. For the data traffic, these features are not important, so AAL 3 and 4 and 5 will not provide it. Instead, they will provide error detection capability, okay? Error detection is important for multimedia, yes and no. If you have an uncompressed signal, like in this example, you can tolerate some losses. If you start reducing the redundancy by compressing the signal, losses becomes typically not acceptable. So you have to deal with losses also for multimedia. Because when you compress the data, the information that you send is really fully needed. If you don't compress, there is a lot of redundancy, and so you can tolerate some losses. So in some cases, you may also need error detection capability, at least detection capability, also for multimedia traffic. It depends on the scenario. Okay? So these are the summary, the set of features that are provided in the convergence sublayers. Not all of the AAL provide all of them. Okay? So you will have some error detection in some of them. You will have some synchronous recovery, sequence numbering, and timestamping. Those three for multimedia only. Okay? Is it clear? Any question, any clarification? Okay, it seems that you are a little bit tired, so it's a good idea to stop it for 5 to 10 minutes, and then we will resume after the break, okay?